Hello. It's time to enter the matrix. Stat world. Ready for your two sample proportions? That's right. Get those notes ready. Here we go. All right. So we know that those conditions are still around. These gatekeepers, they're going to be happening over and over and over. So random. You want to make sure both samples are random, right? Because we're talking about two groups, right? Two proportions. So both samples have to be random. All right. When it comes to normal, ring, ring, who is it? Oh, we know who it is. It's Jake from Stat Farm. We need to make sure that both of these pass. So N1, P hat 1 has to be at least 10. N2, P hat 2 has to be at least 10. And you have to check the flip side, right? So these are the successes. You have 10 successes. And then over here will be the failures. So N1, 1 minus P hat 1. And N2, 1 minus P hat 2. All right. Independent. Of course, if it says it's independent, if it's a experiment and they have random assignment, then we're gonna have independence. But if they're sampling without replacement, then we gotta check it, right? And it's that 10N has to be at least, oh, just kidding, goes this way. All right, so you wanna check it for both, right? You wanna check for both of those groups. All right, you wanna make sure you haven't oversampled from your two groups here. All right, so here's some examples to kind of walk you through it. A veterinarian is studying a certain disease that seems to be affecting male cats more often than female cats. The veterinarian wants to take a sample of male cats and a sample of female cats and make a 2-sample Z interval to estimate the difference between the proportion of males and females that are infected. Which of the following are conditions for this type of interval? Both samples include at least 30, so that's drawing on that central limit theorem, but that's going to be for mu, right, for X bars and averages. This is for proportions, right? It says right here, proportions, so it's not that one. They sample an equal number of male and female cats. Now here's something that's interesting that a lot of people get confused on. When you're taking these two different samples, right, and you're calculating those proportions, they don't have to be the same sized sample. They can be different. Of course, it's nice if you can make it the same, but that is not a requirement. Cats in each sample are randomly selected from their population, yes. All right, so this is the only condition that they listed here that would work. These are examples, by the way, from Khan Academy. So when you get on to Khan Academy later today, you'll maybe see these problems popping up. All right, let's try another one. A sociologist suspects that men are more likely to have received a ticket for speeding than women are. The sociologist wants to sample people and create 2-sample Z interval to estimate the difference between the proportion of men who have received a speeding ticket and the proportion of women who have received a speeding ticket. Which of the following are conditions for this type of interval? The samples both include at least 10 people who have received a speeding ticket and at least 10 people who haven't. Yeah, that's that normal check, Jake from Stat Farm. We have to have 10 successes and 10 failures. Perfect. The people in each sample can be considered independent. Yep, we need that. They take separate random samples of men and women. Yep, random is important. So all 3 of these would have been checked off if you were doing Khan Academy. All right, next page. This is a review. 2-sample Z interval for the difference in proportions we actually did, I believe, a week ago. But I wanted to write it down again so that you had it. Your formula here, we were trying to capture the true difference. So we had our sample plus or minus the margin of error. The margin of error formula is that Z star times the standard error. It was that giant square root. You had P hat 1, 1 minus P hat 1 all over N1 for the first group. And then for your second group, you have P hat 2, 1 minus P hat 2 all over N2. These formulas are on the formula sheet, so it's not something you have to memorize. You can look it up. All right. So moving on, We've got an example that runs through this formula. Jamie is a market researcher interested in nutrition. He suspected that people in the 20 to 29 age group were more likely to say they were vegetarian than people in the 30 to 39 age group. He obtained separate random samples of people from each age group. Here are the results. We want to construct a 99% confidence interval to estimate the difference between 20-year-olds and 30-year-olds who say they are vegetarian. So let's go ahead and get our p-hat for those 20-year-olds. So the 20-year-olds, we had 12 out of 80. All right, let me grab that T.I. Joe because I'm looking at the multiple choice. Everything's as decimals instead of as fractions. 12 out of 80, that would be 0.15. So spot checking down here, 0.15, 0.5, blah, blah, blah. All right, so I can't eliminate any yet from the beginning, but under here I can, because we need this to be a 0.15. So that one's out, that one's out. And then the denominator checks out. The 88, I don't think, let's see, 85, 85, oh, okay, so they're all good. All right, so now we need to check on the 30-year-olds. So the p-hat for our 30-year-olds, 20 of them are vegetarian out of 120. So 12 divided by 120 is 0.10. Should have done that in my head. Neo would be disappointed in me. 0.10 is all the way through. All right, notice over here, well, that one's already gone anyway. 0.10. So this looks okay. Looks okay. This one's not good because it's got a minus. The formula is a plus sign here. So it's between B and D. The only difference now that I'm noticing is the Z star, right? The Z star, your critical value. We can look these up on that T distribution chart that was available on the blog last week. All right. At the very bottom row where there's this infinity symbol, these are your Z stars. So if you look at your Z star, we're looking for a 99% confidence interval. So 99% is 2.576 for our critical value. So 2.576, it looks like my winner chicken dinner is D-dog. Got it? Good. Next page. This is another example with that proportion formula again. We have students and adults using an app. We're going to construct a 95% confidence interval to estimate the difference between teens and adults that use this app. Notice the multiple choice is different from the first one. They went a little bit farther on the formula. All right, first thing I got to get is my sample. So teens, we had 54 teens out of 120. So our sample for teens, 54 out of 120, you get 0.45. Your sample for adults, 26 out of 130. 26 divided by 130, that decimal is 0.2. So when we get to our formula, the formula starts with the subtraction of our samples, teens minus adults. Then it's plus or minus Z star times that giant standard error formula. All right, so teens, 0.45, minus adults, 0.2. That crosses out A. That doesn't help along the way because all of these use 0.25. So now I've got to focus on the margin of error formula. If you recall, that formula is not pretty. It's pretty in depth, actually. So what I recommend is just using T.I. Joe to get our answer, and then we'll work backwards from the interval that's provided. Grab that calculator, head on over to step 1. Test. We have 2 samples. This is an interval. 2 sample T interval. Option B, boy. 2 prop Z int. Hit enter and let's get that data in there. Our teens were 54 out of 120 using this app. Our adults were 26 out of 130 using this app. We want 95% confidence. Calculate. Our interval is 0.13752 to 0.36248. You might ask yourself, Mrs. Hamilton, that does not match here, but we can work our way there. We know the middle of this must be 0.25. So we just need to figure out what's added and subtracted to 0.25 to give us these two results. So I'm going to subtract 36248 and 0.25 on my TI Joe. And I get 0.11248. So the margin of error, 0.112. Our answer is D-dog. Next page. Now we're getting into the new stuff, right? We want to write hypothesis for these. Hypothesis testing, we know from one sample proportions last week. So let's see here. Getting things ready for my matrix. We are ready. We've got Samuel. Samuel suspects that the proportion of American adults who read news primarily from social media is increasing in recent years. He has data on this topic from a random sample. Way to go, Sam. Random, I like it. He wants to test if the proportion of adults who read news primarily from social media was significantly higher in 2017 than it was in 2018. So immediately I'm thinking about that alternative hypothesis. We want 2017 to be a higher proportion than the 2016 proportion. So when we look at our options down below, remember your null hypothesis always, 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 I think there was a glitch in the matrix. Sorry about that. You always want to use the equal to symbol. Notice how D-dog fails. It's using the does not equal to symbol and the null hypothesis. No, thank you. Then I look at my other options. The only one that shows 2017 greater than 2016 is B-boy. Check out Kara. Hey, that's me. Kara works for a website that is considering sending emails with different types of coupons to its customers. She suspects that coupons offering $10 off will be used more often than coupons offering 20% off. She plans on sending each type of coupon to separate random sample of users. She'll then test if the proportion of customers who use the $10 off coupon is significantly larger than the proportion who use 20% off. So we want the $10 off to be larger than the 20% off group. Look at your options, see if we can't narrow it down just by looking. The null hypothesis must be an equal to symbol. So it looks like D-dog is eliminated. All right, so we wrote it this way, $10 greater than 20% off. The multiple choice has everything on the same side. We've done this math before. All we have to do is subtract 20% off. What you do to one side, you do to the other. Subtract 20% off. 20% off minus 20% off is 0. On this side, we have $10 be minus 20% off being greater than 0. So we want 10 minus 20 greater than, that is not the right symbol. $10 minus 20% greater, there we go. So B-boy is our answer. Next. Now we need to figure out the significance. Remember, when we're doing a test statistic, this is when we grab our magnifying glasses and we're looking for evidence. Our evidence is a p-value. In other words, looking in the tails, did we beat the odds? The test statistic in a two sample z-test for proportions looks like this. We're going to find that z-score. Where are we on the bell curve with our sample? Since we have 2 samples, we want to subtract them down to a single number. What's the difference between our 2 samples? We're going to see how far away that is from our null hypothesis. What you may or may not have noticed on these hypotheses is that it's always going to be equaling 0. If I bring everything to the same side, 0 is over here. So we want to see how far away everything is from 0 every time. Now, the denominator, you're not going to like this formula. It's on the formula sheet, so you can look it up. Don't be scared. We've got our giant square root. We got to combine our proportions. Do the complement to our combined proportions. Times 1 over the sample size of N1 plus 1 over the sample size of N2. Did you just die? You're okay. All right. This formula is a little bit crazy. The way we find the combined proportion is by taking our samples and just making it one giant fraction. So the number of successes out of the grand totals. On an AP exam, I don't recommend showing your work. I know that's weird to say, but for this one particular problem, most students will make a mistake. And if you make a mistake, we have to take points off. We don't always necessarily want to see the formula. So if it's not specifically asking for the substitution for this formula, I would back off, right? Back off and just use your TI Joe. Let me run through this so you can see it in action. A large school district was considering changing the start times to its schools. The change would involve high schools starting later and elementary schools starting earlier. The school district was curious if parents supported this change, so they surveyed separate random samples of parents from both types of school in the district. Here are the results: high school versus elementary school. The district wants to use these results to carry out 2 sample z-tests to determine if the proportion of parents who support the change is significantly different. So we're looking for evidence of some significant difference for each type of school. Here's something that's nice. Conditions have been met. You do not, I repeat, you do not have to show your 3 conditions being checked. They have already been met, satisfied. All right, so the first thing you want to do is define what we're after. It's proportion. So we are investigating the true difference in support of time change. And I'll put in parentheses, high school minus elementary school. Our null hypothesis would be, there is no difference, nothing to see here. Keep moving on with your life. So we could say high school minus elementary school is 0, right? No difference. If you remember from the first day, we learned about hypotheses like this. The null hypothesis, H sub O, right? We use the subscript 0 because it's a statement of no difference. So no difference. There's no difference here. But the alternative is what we're after. We're trying to see if they are significantly different. It doesn't matter in which direction. They didn't specify one being greater than the other. We're just looking for any type of difference. So when we compare the difference between these 2 groups, we'll just look for evidence that it's not 0. So this would be any difference. There is no alpha level provided. If there is no cut score, alpha significance level, we will just use 0.05 by default. Conditions have been met. So I'm ready to proceed to the formula. For our formula, we're finding our z-score. We want to know where we are on this bell curve. At this point, on a free response, I would not show the substitution into the formula. Instead, I would just name the test. This is a 2 proportion z-test. All right, so grab your calculators. Let's enter Stat World. We're looking for a 2 proportion z-test. You'll notice on your Stat World tests that the first group are the tests. And if you keep scrolling down, that's when it changes into intervals. So the nets are down here when you want to capture the truth. And then the tests are up here when you're looking for evidence, p-values. So 2 proportion z-test is option number 6 on your calculator. Now we can start putting in the details of our test. We have 54 high schoolers out of 100 that support it. Then we have 24 elementary out of 50 that support it. We're looking for any difference at all. So our alternative is the does not equal to option. Calculate. Turns out we have a z-score of 0.6934. We also have, if you look at your screen, a p-value of 0.488. What does that mean? Let's draw a picture. Billy Bell curve, 0 is in the middle. 1, 2, 3 standard deviations to the right. 1, 2, 3 standard deviations to the left. We are at a z-score of 0.69. So that is about right here. Since this was two-sided, right, two-tailed, it could be on either side, any difference. We also have to do the negative side. So the area under the curve is our p-value. Notice we've shaded quite a lot of area. Almost half of our bell curve has been shaded. Do we have evidence of significance? No. Is this rare? No. So we would say there is no evidence that there's a difference between opinions here. P-value, you always compare it to your alpha. 0.488, is it less than 0.05? No. So we would fail to reject the null hypothesis. All right. Your closing line then, we have insufficient evidence. At alpha equals 0.05 to conclude a difference for each type of school. Again, the only difference when you're writing these sentences is this word. Either you have the evidence and you would say, I have sufficient evidence, or in this case, we don't have the evidence, so we have insufficient evidence. These conclusions always go back and reference your alternative hypothesis, which was that there was any sort of difference, or you can steal this language, significantly different for each type of school. So we have insufficient evidence that alpha equals 0.05 to conclude a difference for each type of school. Let's try one more. A medical researcher was curious if the proportion of adult males who are colorblind is the same in the United States and Great Britain. They obtained separate random samples of records for adult men from each country. Here are the sample results. The researcher wants to use these results to test if the proportion of adult men who are colorblind is significantly different in the two countries. Again, they don't care if one is greater or if one is less. All we want to know is there a difference? Here we go. We're after the true difference in proportion of color blindness. We're going to go in this order. We've got United States minus Great Britain. Our null hypothesis is that there is no difference between them. Your null hypothesis is a statement of no difference, hence the 0 for the subscript. The alternative, we want evidence that, hey, something is going on here. The proportion is somehow, some way different. There is no alpha level provided, so the default is 0.05. We will assume conditions met. Remember conditions random, which the problems did say random. Normal, we have at least 10 that are colorblind and at least 10 that are not colorblind. And independent, well, we'll have to assume that there's at least 3,000 and at least 2,000 men in each of these countries. Safe to assume. Time to run through our formula. We are running a 2-proportion z-test. This is number 6 on your calculator. Enter Stat World. Test number 6, 2-proportion z-test. Ready? We've got 30 that are colorblind in the United States out of 300. We have 10 that are colorblind in Great Britain out of 200. We're looking for any difference at all. Calculate. We have a z-score of 2.0189, a p-value of 0.043494135. I think we have evidence. Conclusion time. Z-score was 2.02 if you round. Your p-value, 0.04. Show it on a bell curve. Zeros in the middle on this standardized z-curve. 1, 2, 3 standard deviations to the right. 1, 2, 3 standard deviations to the left. This is a 2-sided hypothesis test, so we must shade both sides of this bell curve. Go to 2.02 on the right. 2.02 on the left. The area under the curve is 4%. There's a 4% chance of this sample happening 30 and 10. We beat the odds. 4% chance, that shouldn't have happened. We have evidence that this null hypothesis is a lie and that there is a difference between these two groups of men in America and in Great Britain. P-value less than alpha is what you always compare. So is 0.04 less than 0.05? Yes. Since it is, we must reject the null hypothesis. Your sentence, we have sufficient evidence at alpha equals 0.05 to conclude the proportion of adult men who are colorblind is different in the two countries. We have sufficient evidence to conclude the ha. Got it? Good. I know this problem didn't ask for it, but if you wanted to know what the truth was, you could grab your net and scoop for the truth. If you enter Stat World, test, and you go down to the intervals where the truth is, test B, 2 prop Z interval. The data is already in there, 30 Americans out of 300, 10 out of 200 from Great Britain, 95% confidence, yields a positive interval. If the interval is entirely positive, then that must mean that the first number is the larger of the two numbers. So the proportion of men in America, higher levels of color blindness. Why? Why is this? Guess we'll never know. Goodbye for now.